welcome to the stage Vice President and General Manager of NVIDIA's Hyperscale and HPC, Ian Buck.
Thank you. It's an honor, it's a privilege. I feel just blessed to be here at SC25, I will say. I was there for NVIDIA's first supercomputing back in 2006. It was a room much smaller than this and a small session where we first showed CUDA for the first time. And I got to give my first CUDA talk. And to now, we're here and it's been amazing. I've come to supercomputing every year since then, with the exception of COVID, and I've learned and always enjoy talking to every one of you and the customers and the developers here. Supercomputing challenges us. It challenges me. It challenges our roadmap. It's where we try to solve the world's most complicated, hardest problems using computers. And not just regular computers, but computers that are supercomputers. They're time machines. Can we build something that the world's never seen before to solve problems that can't even be seen, to build instruments of science that can zoom in and simulate what no microscope or natural human phenomena or wet lab could ever witness. It also challenges us in our technology. And many of the technologies that you hear about today that make things like ChatGPT successful and giant supercomputers and now at commercial and AI scale happening in Texas, it started here at supercomputing. Working with Tsubame on the first immersion-cooled supercomputer in 2010 with GPUs. Tsubame also was the first supercomputer where we felt like we had to change the form factor. For GPUs back then were PCIe cards, that just like your gaming and graphics card. And for the first time, we realized if we turn the GPU on its side, we can use all of this area, not just this area, for doing I/O and connecting multiple GPUs together. It actually happened here in supercomputing. All of our HBM products were always dedicated toward computing and supercomputing. In fact, one of our first HBM supercomputers was the Peasdane supercomputer in 2016. We learned how to connect CPUs and GPUs together beyond just PCIe, but actually build custom NVLink interconnects, working with IBM on the Open Power systems and the Summit Sierra systems back in 2016, happened here in supercomputing. Building supercomputers that were tightly connected with NVIDIA's first CPU connected to a GPU, the Grace Hopper system, was first announced with the Venado back in 2022. Before the ChatGPT moment, the folks at Los Alamos National Labs decided that new architecture was a great platform, not just for simulation, but also for machine learning and even talk of AI back then. Look at what it's become today. And of course, that led to one of the first supercomputers used by OpenAI, which was 10,000 Volta GPUs. There's a picture of it there. The actual one of the HGX nodes that went into that first supercomputer built by OpenAI in partnership with Microsoft. Supercomputing is where you guys pull us forward, you pull the whole industry forward to build the next and advance the roadmap. With that, we have built an era of accelerated computing. Our first supercomputer was actually in 2008 on the top 500. It was the Tesla S1070, or the K20 GPUs. And today, now 88 of the top 100 supercomputers are now accelerated. That's increased from 82 in June, 90%. So obviously everybody here saw the future and could see why we need to be accelerating computing in order to solve these problems. So today, those first supercomputers, of course, were built for simulation, to build an instrument of science that could simulate something that could not be observed in natural phenomena, either at time scale or macroscopically, microscopically, that only a computer could help understand, visualize, and recreate with simulation. But with the advent of AI, there's an explosion of applying AI to science problems. In 2016, fueled by massive amounts of data, new algorithms, and of course access to GPUs, the AI research world took off not just in consumer and building new models and new ways to talk to computers, but also to apply it for science. And of course now in 2019, with the advent of using these same computers to simulate the future of quantum computing, we've now moved from having just one primary pillar for supercomputing to three. And in this talk, I want to talk a little bit about where are we in the world of advancing simulation, advancing AI for scientific discovery, and the latest in understanding the eventual future of integrating quantum computing into a QPU, GPU, and CPU world together. Today's supercomputers need to excel at all three of these, and the research and work being done is just astounding. The platform, a number of applications now that are accelerated on these domains is exploding. There's over 6,000 CUDA accelerated applications that we've been able to track in every discipline, from life science to material science to nuclear energy, physics, quantum, earth science, CFD, autonomy. The number of applications, some of these names are familiar. They were there when we first came to supercomputing 20 years ago, and today new ones are emerging every day. Using new methods of applied AI or new programming environments, as well as taking the new algorithms of AI and quantum and inserting them into existing algorithms every day. It's one of the joys of my job is I get to work with all of these developers in this ecosystem to figure out how to advance their research, their science, and then bring it to life on these supercomputers. Every one of an NVIDIA supercomputer can run all of these applications and become an instrument for science for as long as it is maintained and run by that center. Our contribution is our libraries and our ecosystem. We call it CUDA-X. It started out in the very beginning with just two libraries, three if you count math.h. The first, of course, was cuBLAS. The second was cuFFT. From there, we've exploded the number of libraries. Our role is to provide a backbone of libraries that people can use in either generic math and solvers to specialized libraries like cuLitho, which is specifically designed for circuit development and computational lithography. For models like cuOpt, which is specifically designed for path planning and routing for solving decision and optimization problems. To doing cuGraph from quantum computing to Earth-2 to MONAI to Parabricks. We now have over 600 million downloads of all of our CUDA-X libraries, tracking about 7 million developers, and about 1,000 SDKs and AI models that can be used in the CUDA-X ecosystem. This platform, these capabilities allow for amazing discoveries that are super cool. One of the Gordon Bell submissions this year is actually on the Jülich Jupiter supercomputer, which I got to enjoy visiting earlier this year. This is Daniel Klake's team at Max Planck Institute for Meteorology. They took an entire Earth climate simulation all the way down to a 1 kilometer resolution around the world, and they ran it on over 20,000 Grace Hopper superchips on the Jupiter supercomputer. They're actually able to simulate the Earth and its carbon, water, and heat cycle, the Earth breathing, at a rate of 146 simulated days every day. Every day they can simulate the Earth and how the Earth breathes for 146 days, roughly a half a year every day. This will take decades, can be simulated in weeks, and it's twice as fast as the world's previous simulation world record. There's so many exciting applications happening in AI physics and acceleration, from simulating jet engines to new kinds of thermal capsules for spaceflight. There's two in particular that are super exciting that I'll go into a little bit more. There's a startup called Luminary Cloud, which is led by Juan Alonso, a former professor at Stanford and an ex-NASA director. Actually, he was one of the first users of GPUs at Stanford when I was there for applying GPUs for CFD simulations. His company actually helped Northrop Grumman to build an AI model for spacecraft control nozzle. That's a nozzle used for a spacecraft. And what they did was they ran about 2,000 CFD cases on a suite of GPUs, varying the different nozzle geometries and flow conditions. And then they used NVIDIA AI physics package called Physics Nemo framework to train an AI model on all that data. So when they're all done, they now have an AI model which now can actually run in real time in less than 5 seconds to do a simulation that took on the order of hours before, and it's within a 5% error. So it allows Northrop Grumman to actually explore the space of rocket nozzles using a proxy model of AI to pare down all the different possible geometries to then run and dive deeper and to do a full-fledged CFD simulation. NASCAR is another one. They're doing, obviously, CFD of a racing car. This is a 180 million cell simulation running on 192 cores with OpenFOAM. It takes about 11 hours, but using, with Star CCM+, using a single GB200 node, they can actually run this model in about 48 minutes. They're using a mixed precision of both FP32 and FP64 emulated in order to get to actually produce the turbulent flow across the race car in order to get those results. The applied physics of modern accelerated computing really is accelerating the path to discovery. One of the software ways that we're helping do this at NVIDIA is actually put out more libraries and more programming environments to make this easier. The one we're talking about here at Supercomputing actually is called NVIDIA Warp. NVIDIA Warp is actually a Python package. It has all of our math libraries, all of our simulation. It allows you to write your physics in Python, which, of course, many of the developers today are now using, in addition to C++ and Fortran. What's interesting about Warp, though, is the library and programming environment is designed to be automatically differentiable. What that means is you can describe the physics of a ball bouncing on the ground, its elastic properties, where the wall is, and how it should respond, and run the simulation. But because it's auto-differentiable, you can immediately plug it in to PyTorch or JAX, and then run a solver on it, because you've expressed the computation in a way that the program is known to be differentiable. That way, you can actually have it simulate and run and solve for what is the initial velocity and direction of the ball in order to hit the black box. That happens automatically for you. This is taking an idea, taking an idea from AI and now applying it to physics and being able to provide a very simple, friendly environment. I would totally encourage all the developers in the audience to go check out Warp. We have I think they're showing it in the booth, but it's also free and totally downloadable off of our website. And fun to watch as well. Of course, AI is also transforming how science is done. We're tracking and involved in many projects. There's too many to actually down-pair and put on this slide. From building agents for the ICF, astrophysics at Argonne, seismology, we'll talk about, that's a great example. Drug discovery and weather modeling and building open models for science. It's being applied across so many different areas. Specifically, the seismology example at UT Texas Austin, that is a picture of the Cascadia subduction zone. So I live in the Bay Area. We're all familiar with the San Andreas Fault, Loma Prieta, and earthquakes. There's also a very, 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 very big fault right outside of Seattle in the Pacific Northwest. It's only about 100 miles from the coastline. And of course, the big risk of a rupture there is a tsunami, which will be very close to Vancouver, Seattle, and the surrounding areas. Folks at the University of Texas Austin, along with Lawrence Livermore and the University of California, San Diego, have built a digital twin to actually do real-time probabilistic tsunami forecast. They built a 1 billion parameter surrogate model, and they trained it on the seismic and tsunami data from 15 years of data from the Neptune Cable Seismic Observatory. Basically, they took all of the measured data from 15 years, trained a model, and as a result, they can actually apply that model in real time to all of the seismic events that happen along this specific fault. 100 miles is not very long, and now by using AI, they can actually predict whether an earthquake will generate tsunami, how big it'll be, and identify public safety immediately based upon whether if it's a real or false alarm, and quickly get people to safety. I wanted to show you one more, General Atomics. So General Atomics is developing a digital twin of their fusion reactor, General Dynamics, I should say. And this is actually a real-time interactive digital twin for fusion energy. Never before has anyone built an interactive digital twin of a reactor of this scale. So we have a video of that. I'd love to show it to you.
For decades, fusion energy, the process that powers the sun, has been one of science's greatest opportunities. Cracking it would give us a safe, clean, and virtually unlimited source of power. Controlling plasma hotter than the sun's core means solving physics so complex that even the fastest supercomputers struggle to simulate it. At the forefront of this effort, General Atomics researchers and international partners at the D3D National Fusion Facility are using AI to push fusion research forward. The team is building a fully interactive digital twin of the D3D tokamak inside NVIDIA Omniverse. It fuses sensor data, physics simulations, engineering, and AI models, creating a virtual reactor that can quickly inform decisions. Key controls can be explored in the digital twin to refine the science before running real experiments. These surrogate models, trained on decades of real-world datasets and running on NVIDIA GPUs, deliver accurate predictions at unprecedented speed. This is a platform to optimize reactor designs, accelerate commercial fusion, and make the sun's power programmable.
The opportunity for AI, taking what would normally take days or hours or even an unfathomable amount of compute time, and bring it real time. Not to replace it, but to allow scientists to do that kind of discovery in real time, to explore that search space. And that pattern we see it repeating over and over again. It allows people to discover and to process data that couldn't be processed in real time ever before. One of our goals is to provide platforms and softwares and boost the capabilities of scientists by building not just libraries, but also frameworks in order to accelerate those discoveries. One of which is NVIDIA Holoscan. This is the Meerkat Array. It is a 64-dish radio telescope in South Africa. It's a precursor to the Square Kilometre Array, or SKA, that many of you know. It is consuming about 2.1 terabits a second of continuous observation data. Data that it's just coming in so fast it's impossible to process in real time. But Holoscan is a software package that allows us to actually take the data streamed live over an InfiniBand or dedicated FPGA-based Ethernet interconnect and stream it directly into a GB200 NVL72 rack. That allows it, and then immediately run AI pre-filtering on it to detect and identify the interesting signals and whittle that down, that 2.1 terabits of data, into stuff that should be processed further for discovery in radio astronomy. Another one of our packages is NVIDIA Alchemy. NVIDIA Alchemy is designed for chemistry and material science, building AI models that actually help scientists predict possible new kinds of materials and their properties as you search the space of all possible materials. And this is any kind of metal, any kind of material, any kind of plastic and frankly, the number of possible materials in the world is greater than the number of atoms in the universe. The search space is huge. Using NVIDIA Alchemy, which comes with a variety of different pre-programmed or pre-trained models for material science, we can actually use them to search the space of all possible chemicals out there for specific workloads. One of them, with ENEOS, is actually looking for a next-generation cooling liquid for immersion-based cooling. Many of the cooling fluids today that are immersion-based use quite toxic PFAS materials, finding a environmentally safe, yet also electrically inert and have good dielectric properties, as well as corrosion and longevity properties, have all those materials. is a vast search space. By using Alchemy, they can actually pre-process potential candidates, a huge volume of them, send them through the AI model, whittle down what would be tens of thousands of possible chemicals down to only a few hundred to then go explore and do further research. Very cool. I encourage both of you to check out HoloScan and Alchemy, both open source and available from NVIDIA. And I think there's some demos we have down on the show floor. Okay. In addition to software packages, there's, of course, models. And there are many open models now in the world. Hugging Face has thousands and thousands of models. We're now seeing NVIDIA also is trying to build models to help advance different areas of industry. We've announced models for robotics called Groot, Cosmos for physical AI, Nemotron, which is our own large language model for agentic AI and chat, and Clara for biomedical. Here at Supercomputing, actually today, we're announcing another family of models, which we call Apollo. Apollo is a dedicated set of models which are designed for AI-based physics. These are pre-trained models, and they come also with reference workflows for how to fine-tune them and run them for inference. It allows you to train your own model for your particular physics use case. We're focused in basic, simple areas common to all of us, which is CFD and aero and manufacturing, et cetera, but also looking at structural FEA programs like crash codes, consumer electronics, and weather and semiconductor use cases. With these models, we're hoping to move and, again, apply the same technique, taking AI and making it a predictor for search space exploration and make something that was offline real time. We have one model that we've actually trained, and I can go show you that. This is actually one of our first models built for Apollo. This is specifically focused on the high lift, low speed design of an aircraft wing. Right at takeoff, when you have the flaps down at a high pitch, is one of the most turbulent and flow separation critical parts of aircraft or wing design, and you need high quality LES simulations. Running the Charles CFD code developed at Stanford by Parviz Moin, which is now part of Cadence, we actually partnered with them to actually simulate 8 hours on 32 GB200 GPUs for a 300 mil cell use case, and then modified the geometry and ran another 8 hours, modified the geometry, and generated a sampling data set for this airplane wing in this specific use case. We ran nearly 2,000 simulations and generated 40 terabytes of data, and that created a training set for Apollo. We then took the model, trained it on GB200s, and turned what would normally take an 8-hour simulation down to just 5 seconds on an RTX GPU. This Apollo model now is interactive, and the pre-trained model is going to be made available. It's going to be made open along with all the software in order to run it, and the instructions and reference workflows to how to fine-tune the model for your particular airflow use case. We'll be adding more models, of course, to Apollo, and specifically focused on automotive crash, EDA, and other areas of CFD. It's an amazing demo, and I encourage you to actually check it out. This is actually real time, running the model on an NVIDIA GPU, and the designer can actually change the pitch, the airflow, the angle. We can actually also change the geometry. So it's not just on a fixed geometry, but we can actually change the angle of the flap, the angle of the wing, or the actual shape of the flap all in real time. This allows the aircraft engineer or designer to actually explore the whole space and observe certain different kinds of phenomena, tag them for further study, for more in-depth simulation as a result. Very cool, and very excited about Apollo, and check it out. We talked about simulation, we talked about AI. The third that's happening right now, of course, is quantum. Every GPU supercomputer right now is playing a role in figuring out the next chapter of computer science, which is quantum computing. Quantum computing, we haven't even written CS 101 yet. We have like Shor's algorithm, but we don't have the sort, the data structures, all the different ways of applying and doing solvers are so different. We're starting from really a blank notebook. And in order to do that, we have to give the researchers, the people to figure out how to turn spin into a solver. An incredibly hard problem, and as we scale it up and as we wait for the production at scale logical bit quantum computers to become ready, every GPU supercomputer is being used now to actually explore the space and figure out what are the algorithms, what are the building blocks, what are the foundations of computer science in this new quantum world. There's some amazing work being done in quantum. One of the records set actually was on Jülich, on those 20,000 Grace Hopper system. They actually set the record for the largest simulation of Shor's algorithm, 50 qubits. The previous was 48. That's 2 orders of magnitude larger simulation of the Shor's algorithm. And how do you scale it across that system? Require them to actually build a custom design communication and job scheduling stack in order to actually run the algorithm at that scale. In addition to breaking records and figuring out how to scale up and build new algorithms, we're also learning how to build these chips. How do you build a quantum processor? There's no synopsis for quantum chips. There's no cadence for quantum chips. They don't behave at all like traditional silicon. And in fact, they have a wide variety of different technologies. This is work actually being done on the Perlmutter supercomputer. It was actually the world's first full chip simulation of an entire QPU run on 6,724 GPUs. Basically, this is the first EDA simulation ever of an entire quantum processor. It was built using NVIDIA Q Dynamics and Q Density Mat. There's a whole library of Q libraries as part of NVIDIA Quantum in order to accelerate this workspace. And finally, we are starting to get logical qubits that allow us to explore what the future of supercomputing is going to look like. One of the challenges, of course, how do we connect a quantum processor with a GPU supercomputer? Quantum processors are not going to run every workload, but they're going to be a critical tool in doing parts of our calculations in order to solve the problems we're looking for. With that, we announced back in GTC-DC the NVIDIA Q-Link, which is basically a reference architecture, a design of how to actually process the incredibly noisy signals coming off of quantum processors and be able to process that signal to look to see if we had the correct superposition and able to execute and run the quantum circuit. This was done in partnership with the entire quantum ecosystem, the builders of these quantum processors. And here at Supercomputing, we're actually announcing that we've actually been working with the supercomputing centers worldwide that are also, of course, dedicated, interested in building the next generation quantum QPU, CPU, GPU supercomputers and how to connect them to their particular research area or deployed platform for quantum computing. So we expanded our support and actually working with 23 different supercomputing centers worldwide, too many to name, but to help start the next chapter of supercomputing, which now includes quantum computing. Okay, stepping back, where are we today? This world is changing so fast. I used to, supercomputing was one chapter every year. Now every day there's another breakthrough, another supercomputer announced, whether it be for developing the next world model from OpenAI to discovering the next breakthrough in radio astronomy. The number of computers also are exploding. This is actually a plot of the total cumulative AI exaflops in the world. In fact, we just announced the Vision, Mission, Equinox, and Solstice systems. And also this year in Japan, I got to be there for announcing that Fugaku Next will be built using NVIDIA GPUs along with Fujitsu and NVLink in order to build Japan's next supercomputer. As a result, we now have over 4.5 zettaflops of AI announced with over 300,000 plus GPUs and growing. Truly amazing to see how fast this world is expanding and how quickly we're accelerating these systems and building new ones. And of course, they're getting just bigger. This is the Argonne National Labs Solstice system, which was announced just a few weeks ago. It'll be 100,000 Blackwell GPUs. That is actually more AI than the entire top 500 today, 1.6x actually, and will be the largest AI supercomputer in the entire DOE. And we have folks from Argonne will be joining us today and tell us a little bit more about it. Truly an amazing and impressive system when it gets built. We also, of course, have announced systems at RIKEN. RIKEN, of course, is going to host Fugaku Next. We have 2 systems that are actually being announced in anticipation of the Fugaku Next system, which will come later this decade. One will be focused on AI for science and developing AI for science for seismology, robotics, and manufacturing. The other system is dedicated for quantum HPC and developing the next algorithm of hybrid computing. What problems can be solved in GPUs, QPUs, and working together in order to solve some of the next generation problems that quantum computing will let us solve. It'll be both these will be based on the GB200 NVL4 architecture. So just like we have NVL72, we have NVL4, which goes across rack. A different configuration of the same technology. Of course, all of our software stacks run on all of it. So next, we'll talk about New Horizon. So New Horizon is actually the TACC supercomputer, which we built on GB200, and actually have a dedicated 9,000 CPU-only Vera partition of NVIDIA's Vera CPU cluster. Let's roll the video of Horizon.
Science faces challenges of incredible scale, whether it's understanding our universe or deciphering the human genome to develop new medicines. To take on these challenges, Horizon is being built in Round Rock, Texas. The largest academic supercomputer in the US and part of the NSF's new leadership class computing facility, Horizon will be powered by NVIDIA technologies, Grace Blackwell superchips, Vera CPUs, and Quantum X 800 InfiniBand to advance scientific AI and simulation. Its foundation will be Dell Integrated Rack Scalable Systems, featuring Dell PowerEdge servers. With 100 times the AI performance of the Frontera supercomputer, Horizon will provide unprecedented power for science. At its heart is the NSF's Characteristic Science Applications program, large-scale science projects that are shaping Horizon from the ground up. Biochemists like Ahmad Taj Khorshid will use Horizon to simulate viral infections. Astrophysicists like Tom Quinn will trace the evolution of galaxies. And geophysicists like Yifeng Sui will advance earthquake modeling to improve seismic hazard maps. The Horizon supercomputer will support up to 15,000 global researchers a year on NSF-funded projects, accelerating the most innovative, high-impact initiatives to fuel discoveries not otherwise possible.
Really excited to see Horizon come to life. It's been a project that we've been working on with Dan at TACC, and he'll join us later. We can talk more about it. Building not just a supercomputer that's built with the same infrastructure, same guts, same brains as for AI and simulation, but also one of our first large-scale Vera CPU supercomputers for the CPU workloads. And we'll talk a little bit more about Vera in a sec. Our goal in general is to build a platform that innovates every year, but not just to the hardware, but actually compounds and provides a multiplicative effect on top of from taking the floating point capabilities to the raw compute, the architecture, compounded with the memory, up to bring it all together with NVLink and connect it at scale with networking, and of course, beyond that, of course, all of the software to activate it. We're on a yearly cadence now. It started in the beginning with many of the systems that were Volta that really put us on the map, to now Blackwell, to Rubin, and the next generation Feynman. Our innovation space is where we build silicon in order to connect all of that supercomputer together to provide the best possible platform for building supercomputers, whether it be for consumer AI, or for HPC, or for supercomputing. And each one of them can be tailored and designed into the form factor in the rack that makes sense for that customer and that environment. And today, we've got a couple of additional announcements. What makes it all connect together, though, is really NVLink. When we went from Pascal to Volta to Ampere to Hopper, well, the key part that made things possible was how do we connect all those processors together. Not by, initially, with point-to-point, we were sharing that connection, that perimeter of that chip with every other chip, and it limited our communication. A big step was actually building an NVLink all-to-all switch where every chip running at 1.8 terabytes a second of I/O can talk to any other chip all through that NVLink switch. It's not really a switch. It is a shared memory fabric. We can't just take an Ethernet switch and scale it up. Ethernet was designed for large radix, quite large packets, and really a throughput kind of network. NVLink is actually an entirely different piece of silicon, a different architecture, and we actually have, not based at all on the Spectrum Ethernet that we have today. We designed for the fastest possible, lowest latency, and highest throughput message passing in order to build a giant shared GPU. That lets us do some amazing things. This is a graph from SemiAnalysis that did a benchmark called Inference Max. They basically downloaded and took the latest DeepSeek R1 model, and they downloaded the latest open source SG-Lang framework, and they just measured it across a Pareto. What is the interactivity rate you want in order to how fast to run the model? You want from a token rate, and then measured us the total throughput per GPU. Obviously, if you want to run the model slowly, we can amortize it across multiple GPUs and run multiple copies, which is a little more efficient versus running at the max token rate, where we take all the GPUs and dedicate it to you, that one user. There was a 10x performance increase from Hopper. It wasn't because Blackwell had 10 times more floating point. Actually, it only has about 3 times more floating point. But because we were able to connect all of those GPUs together with NVLink, on a per GPU basis, this is not the same number of GPUs, got a 10x performance improvement. That improves the economics of per dollar by 10x, and improves the per watt by 10x, it improves the throughput by 10x, and for commercial customers who are actually making money on all these tokens, actually generates 10 times more revenue for their AI factory. NVLink has been a huge game changer for us. We continue to invest in NVLink. We continue to explore how far. 72 is just the beginning. We've actually announced that in the Rubin Ultra generation, we're going to go to 576 chips. We'll all be connected with NVLink 72. Oh, sorry, with 576 NVLink interconnect. And the challenge at that point just becomes the one that is no stranger in supercomputing, the mechanical and details of how do you put that many GPUs together at that fast a speed, ideally entirely in copper where it can be affordable yet performant. We're also moving to co-packaged optics. One of the challenges that is familiar in supercomputing and is familiar now in supercomputing in the commercial space is how do we connect these many GPUs together east to west across the entire data center of hundreds of thousands of GPUs and do so reliably and extract and also power from a power efficient standpoint. Co-packaged optics allows us to move the transceiver, little laser basically at every port, and put it right next to the switch chip. That takes that 20-watt laser and using some pretty impressive physics actually takes the wattage all the way down, almost eliminates it, because you're right next to, takes the laser light right next to that chip. That 20 watts doesn't sound like a lot, but you have literally millions of those lasers in a modern 100,000 GPU data center, trying to actually talk all at the same time, generating a lot of heat, and that's costing you in power and in capability of your data center. It also dramatically increases reliability. Co-packaged optics uses an external laser. It's a constant light source. It's not turning on and off or blinking anymore, and it's actually modulated right at the chip. So as a result, we're going to be bringing this to market next year, starting with the InfiniBand, and actually first customers are CoreWeave Lambda and the TACC. With Dan, we'll be building a prototype cluster with the NVIDIA Quantum X Photonics InfiniBand switch. We've also been expanding the NVLink ecosystem further with NVLink Fusion. NVLink Fusion is both an IP package that allows us to actually allow folks to build third-party CPUs or third-party accelerators and connect them and tap them into our NVLink ecosystem. It's a set of IP and silicon technology, and we have multiple partners. At supercomputing, we're announcing that ARM now has joined the NVLink ecosystem. So in addition to other CPU providers like Fujitsu, Intel, and Qualcomm, Fujitsu, by the way, is also a partner for the Fugaku Next system, and their CPU will be used for along with NVIDIA GPUs. ARM also is now has joined, so that means that folks building their own ARM CPU or using ARM IP can actually have access to NVLink Fusion and be able to connect that CPU, that ARM CPU, to an NVIDIA GPU or to the rest of the NVLink ecosystem that's happening at the racks and scale-up infrastructure. As I mentioned, we're also bringing to market Vera. So Vera, we have it over here, is NVIDIA's next generation CPU. It's the one after Grace. What's interesting about Vera is that this time it's entirely NVIDIA engineered core. We call it Olympus. The previous Grace leveraged the Neoverse core from ARM. This is of our own design. We took the fabric that connected all the ARM cores in Grace, we beefed it up, and then we implemented our own ARM core. It actually has twice the performance of Grace. As a result, it supports 1.2 terabytes a second of LPDDR memory. That's all the memory you can see around the die. Using LPDDR5X, which is memory that was originally designed for mobile phones. It's designed to be very low power. The X added all the data center features, the resiliency and ECC and other things, to basically provide that low energy efficient but high bandwidth memory throughput that makes Vera so capable. It also supports chip-to-chip. So there's an NVLink 1.5 terabyte a second chip-to-chip bandwidth between the Vera and itself and other GPUs, making it 1.8x more energy efficient for CFD codes that have been benchmarked, as well as 1.7 on some of the weather codes. And definitely something very cool and be part of the TACC Horizon supercomputer. With that, I wanted to wrap up. Overall, today, the world's supercomputing ecosystem runs 3 workloads. It's simulation, it's AI, and it's quantum. Whether, for whatever reason, the system is originally built and its original mission, every one of those GPU supercomputers that we're enjoying today, they can trust on the NVIDIA ecosystem to continue to advance these 3 fields with over 1,000 SDKs and models to all the scientists and what they can run and the scale at which they can run it. Our new announcement is that this show is, of course, building new models, new open models, not just from NVIDIA, but from the entire ecosystem of Apollo, to build and connect instruments to these supercomputers like we can with Holoscan, to connect them with next generation co-packaged optics and photonics with InfiniBand, and to build next generation quantum GPU, CPU supercomputers with NVQLink. It's driving a just massive tidal wave of new systems. 80 new systems were announced today in the top 500. Over 300,000 total GPUs have been announced with over 2 zettaflops of compute just added this year. Super excited to see that. And with that, I'm gonna wrap up. It's an amazing time at supercomputing. It's an amazing time to be here. I see many of my friends that I've seen for over 2 decades coming to this show, and so many new friends, both new young talent, new scientists. I gotta say, there's also a lot of friends I see from my hyperscale showing up here. You guys have their attention. They came from this community, they're studying it, and we're advancing the entire world's computing together and here at Supercomputing, which is so exciting. With that, I'm gonna wrap up, but I'm gonna invite some of our panelists on stage. So we're gonna do a panel here. I have 4 people joining me today, many of which I've worked with for a lot of my career. Thomas Lippert, who's the director for the Jülich Supercomputer Center. We have Jini Ramprakash from Argonne National Laboratory, which will be hosting the Solstice supercomputer. Dan Stanzione, you saw in the video, is the executive director from the Texas Advanced Computing Center and hosting Horizon. And Mohamed Wahib, who's the team principal from the RIKEN Center for Computational Science, which will also be building Fugaku Next. So with that, I welcome on stage. Good to see you, Thomas. Thank you. Good to see you. Nice to see you.
Thanks, Ian.
Dan, you made it. Hi, Dan. Well, thanks, guys, for joining me today. I think it's been quite a journey, and of course, we've all built some amazing computers. You guys have. It's a real pleasure to be here. So with this panel, I wanted to address some and touch on some of the topics that are happening right now, and really hear some how is simulation, how is quantum, how is AI affecting or changing supercomputing. So with that, I'm going to start with Wahib. Certainly, RIKEN is at the forefront of applying AI to simulation. So maybe can you elaborate a little bit more the way you see science being done? You've been involved for quite some time in this area. So how is it changing today?
Yeah, so thank you for inviting me. So about the question of transformation, it's happening fast, as you just explained. And more or less in the near future, you would imagine that AI would be an integral tool for science. And when I say science, I don't mean just computational science. I mean science at large. And this is very important, because there's a lot of newcomers from different fields of science that are suddenly interested, who historically were not using supercomputers, HPC.
Right.
But those are a lot of fields of science. So that is a big transition we're seeing. And I think it's, you can break it down probably if you want to break it down into a few points. One of it is you start to see, traditionally moving away from modeling simulation design to more like hybrid workflows where you have AI and HPC being coupled. And that can take different forms. It could be like HPC in the driving seat, using AI for surrogates or any predictive modeling or generative AI. Or you can see it the other way around, where AI takes a charge, and then HPC modeling is using in a form of an agentic form. And it will probably expand through different areas. And again, it will take different forms. It will also impact different areas on different levels. The second one is, I guess, HPC has historically, we have looked at it as a more compute-centric view and not a data-centric view. Some niche areas within HPC cared about data, but by and large, it was very compute-centric. As we move forward and AI becomes more integrated, when you have this hybrids and coupling of HPC and AI, it will be more about data handling, data management, the ecosystem around data itself. So you transition from a compute-centric view into a data-centric view, which requires a lot of effort outside the traditional stack and ecosystem we had in HPC. One last thing I think is historically, the way you use supercomputers now, or you have used it until now, is you just write a job, batch job, you submit, it comes back. I guess it's a legacy of how we looked at supercomputers. They were basically designed and looked at as if they're a scientific instrument, like a telescope, for example. You get some slice of time, submit your job, you get your result back. But if you assume that AI was HPC has a coupled workflow, then you would imagine there's a more interactive, not because AI makes it faster only, but because of how the nature of this workflow would look like. So you would basically transition from a batch system into an interactive system. HPC has flirted with that idea for a long time, and some systems even provide some sort of interactive nodes and so on, but it has always been limited to debugging and testing. But I guess this is where the direction it goes.
Yeah, there's a whole ecosystem of just job scheduling. Yes. We talk about Slurm, but then there's Slurmernettes and all the different ways. And then that, grabbing a node and treating it as interactive was an exception. Now it's kind of it's a whole, how do we manage a supercomputer in this new world? So Dan, I wanted to give you an opportunity to talk a little bit about, you've been at TACC for quite some time. The workloads and the libraries that are being applied to some of these problems is expanding. So maybe you could touch base a little bit about some of the stack up that you're seeing and the kinds of libraries that are being used to apply to these problems.
Yeah, so thanks, Ian. You showed hundreds of applications in your slides just a minute ago, right? That NVIDIA has worked on. We see thousands across the sciences, and it's sort of hubris to think any one person could have the expertise to look at all of that by themselves, despite the tendency of every grad student to want to start with and write every single line of code from the ground up. But there's just a huge difference between, understanding quantum mechanics and the physics that you want to represent versus understanding the optimal way to use an NVLink switch to do an all-to-all communication, and the optimal way to fill the buffers to do a Fourier transform in a modern CUDA core or tensor core. I think I read in a Spectrum article recently that somebody did an analysis of just like a smart home garage door opener, and there's 17 million lines of code that it links to. And that's horrifying for a whole bunch of reasons, but so many opportunities for things to go wrong. But that is sort of modern applications, and that's a really simple problem, right? And in these science problems, we have a huge diversity of problems, and they're among the most complicated physics problems in the world, right? So being able to, libraries, at least in theory, have always been the way we sort of encapsulate our expertise and share knowledge, right, between these sort of different levels of abstraction. And so, I'm actually teaching a course this semester that I'm not teaching tomorrow because we're here. But they're getting a lecture on Petsy. But part of it has been you can't build at that level anymore, right? And how do we incorporate AI into the coding place? Basically told them to not write unit tests, let the AI do it. But but all of it is built on find the best library, build on top of that, and tune rather than try and build, from the very lowest level up, and you'll never get anywhere, right? I mean, there's just too much complexity. So, we've moved from this era of having really good libraries for things, the basic mathematical operations, the matrix multiplies, the linear algebra, the Fourier transforms, to these more domain-specific, and giving us this abstraction. It's a perfect way for us to plug in mixed precision algorithms or surrogate models or some of the other abstractions that we need without refactoring the whole code. So, I mean, there's an incredible number of them, and many thanks to NVIDIA for the many you are enabling at this point. But we just can't make progress at the same speed without them.
I learn about a new library every day. You got to study Thunder Kittens the other day. They come up with some interesting names for the libraries out there. But that's how these interactions happen, right? There's a researcher over here and a researcher who maybe is an expert in a particular area and a scientist of the problem. It starts in collaboration, which now actually is happening in totally open source. One of the things about AI is it came alive during the open source revolution, during GitHub. And those libraries aren't just, they're where everybody meets and gathers and can be applied. So I definitely heed your advice to everyone out there. There's probably a library written somewhere, and you just got to look for it to enable to apply these problems. So Jini, Argonne's been around for quite some time, one of the original DOE labs. And I can remember my first visit to Argonne and looking at the Blue Gene supercomputers to now Solstice. So maybe some perspective on how supercomputers have changed and where they're going, given Argonne's rich and long history.
Yeah, so thanks for having me here. And as you pointed out, Argonne has a long and rich history, especially with supercomputing, and there's been an incredible body of work done by many people, my predecessors, and we have our own set of challenges that we are looking at ahead of us. But in some sense, the challenges for standing up these massive supercomputers are very similar to what we faced before. The power and the cooling and the way vendors like NVIDIA and others are headed, the energy efficiency piece of it becomes the most critical thing to solve before we can stand up these massive machines. And then, classic problems, I do a lot of tours at Argonne, so I talk to a wide variety of people, but the one thing that you have to start with when it's a layperson coming into Argonne is what makes a supercomputer super? Why are these called supercomputers and not just stacks of machines that are just there? And obviously the networking plays such a huge role in these massive machines, and especially as we talk about the scale at which we want to operate these machines, the scale at which we want to run our user community wants to run on these systems, those are the challenges that teams of people at ALCF, where I'm working, are looking at for our future machines. So definitely the power and cooling as a basis of infrastructure needs, and given how the entire market is trending, like the power trends are right now, they're just shooting up. That's going to be one of the biggest challenges for us to address.
Totally. The world is, I'm not sure you're competing for power, but now the world's trying to bring online more power, more infrastructure, more shells. And the public-private partnership is one way to take advantage of that ramp, especially at Argonne. So Thomas, AI is obviously a new way of applying computation to scientific discovery, but there's a lot of different kinds of models and a lot of different tools, and some of it is still, the textbooks are still literally being written or being figured out or taught. So how do you, at Jülich, and based on your interactions with the researchers and also industry, kind of decide what tool, what model, how to fine-tune? How do you make sense of the latest?
Yeah, first, thanks for inviting me. Of course. Jülich goes with AI back for several years, and we have some experience with models and foundation models. We had the Joules, I have the Joules machine with 4,000 A100 GPUs. This put us into a position to do something. And what I can say is that we have, meanwhile, about 25 projects in science, and I'm especially happy that you were so much emphasizing on science today. In science, where we see that people are interested to create such models. Just to name a few, this is, for instance, in material science, all this goes via the German Helmholtz Association, and running on our machines, and we hope for the future, of course, that Jupyter will be give us a leap in performance in this direction. And to name a few, like material science or like meteorology or climatology, and especially also in biology, things are moving forward. One prominent foundation or even frontier model will be a frontier model of the human brain. We have the most refined data of the anatomy of the human brain that can serve as a basis, as the basis for such a frontier model where you put all modalities on top of that. And here you see the difference. You asked for how we choose the different criteria. Such models stand for themselves. They are sui generis because you have enough data. You have petabytes of data of the brain, and petabytes of data to put on top of the structures that you create here. This will be very decisive for understanding the unknowns of the brain, so that you can interpolate there. So this is just one very important application, and others are chosen according to the question, does the transfer capabilities of maybe open models or language models can help if they are refined with scientific data. Right. So we have about 14 or 15 of those projects currently running on our machines.
Cool. I mean, certainly I can remember the Human Brain Project, which is one of the impetuses for the Joules Booster. And how many scientific studies or explorations or work done on supercomputers have generated all this data. Now is an opportunity for that lowly grad student to dust it off, and maybe you've built a model for the first time the world's ever seen to actually emulate or reconstruct the neuroscience of the brain. It's wherever there's data, there's a PhD thesis waiting to happen. Jini, it'd be good to elaborate, and I get a lot of questions about this new direction of public-private partnership. What made some of those supercomputers that we just talked about possible was a new way of actually putting it together and leveraging some of the technologies from the cloud. So could you elaborate a little bit more about Solstice in general? How does it work? How does it work?
So, obviously, the announcement at GTC, was the big reveal for the plan to have the 10,000 GPU, and then which we're calling Equinox, and then the 100,000 GPU, which we're calling Solstice. that was the big reveal. And then now we are off trying to figure out all the details under the hood, right? So we're still, obviously, we're partnering with NVIDIA and Oracle on these systems, and our hope is that we can combine the expertise that we bring from the DOE ecosystem. As you pointed out, we have a long and rich history of supercomputing, so we've learned a thing or two with all those various different machines that we've built and the different things that we've had to deal with as we stand up these massive systems. And so bringing in some of that expertise along with some of the infrastructure constraints that I was just talking about, the power, the cooling, the space, and everything that goes along with how do you host these machines at the national lab? And that's the part of the partnership that we're hoping to bring to the table. And of course, Oracle and NVIDIA have also built in the last, 30 years, I guess, a huge amount of knowledge as well as a huge amount of the work that they've been doing on their end as well. So, I'm very excited to see where Equinox and Solstice will go. Very challenging, but very exciting times. The exciting and the challenging kind of war with each other every day. But the idea behind the public-private partnership is a really good one to bring together people with various different expertise and to bring to fruition, trying to maximize the stuff that each one of us can get out of it.
Exactly.
Right? So that's the point behind it.
it wouldn't be a supercomputer if it wasn't hard. And it's what makes supercomputers a supercomputer is not just the technology, but the general. This is not something for the faint of heart. Right. Putting together that kind of system. I am personally excited about it, as supercomputing and HPC in this community has been interested in taking advantage and leveraging what the cloud has to offer. And in fact, we've had some cloud supercomputers. Eagle is a top 10 supercomputer built by Microsoft that's on the list. But what's exciting here, it never really had that breakthrough moment that we have now, where we can take the expertise from an Oracle who's building Stargate in Texas and knows how to deploy at supercomputing scale a supercomputer for OpenAI, and then bring that talent, that expertise of assembly, manufacturing, and operating to the Office of Science, to the U.S. leadership in scientific computing. And we know how to do it, so we just have to figure out the rest of those details. Yeah. Similarly, Thomas, in Europe, there's a lot of excitement about the future of AI factories and the growth, the mission that Europe is on for the next click of computing at scale for AI. So can you elaborate in a similar way what you're seeing in Europe?
So the European efforts in AI factories go back, of course, to announcements of the President von der Leyen. And I think Europe reacted very quickly on the needs to create the environment around its supercomputers. Originally starting also from the scientific aspects, but including also business and economy. Yeah. And the AI factories, meanwhile, we have about 20 of those starting. These are just the surroundings around the European supercomputers, but many of them are already equipped with GPUs and can do a lot in this direction. Jupyter is one of those examples with the Jupyter AI factory. But on top of that, we will see now a sort of unprecedented movement in Europe, going for 4 to 5 so-called gigafactories that are private-public partnerships, as we just heard here. So this is very similar, and these gigafactories are also on the order of 100,000 GPUs. For reference, I don't know if it is Blackwell or whatsoever, yeah? But order of 100,000 GPUs. And so we will see also big efforts from European countries. We had 76 expressions of interest of different organizations all around Europe to build such type of infrastructure and to go forward here. Among them, very prominent and potent European companies. So we will see something, and I hope that this will be all fruitful also for the development of the European AI landscape.
Well, I certainly enjoyed watching and attending the Jülich launch. And with the German Chancellor there and the also EU Commission presence, you could see how computing, supercomputing, and AI is a matter of national importance for the whole continent. Being able to take a nation's data and apply it to the problems of their people, their economies, their manufacturing as a place of leadership. Supercomputing now is elevated to this new tier of national importance. The one place where there's been the most example, actually, of applying supercomputing to a nation's problems, I think, actually, is Japan. I certainly remember the ABCI supercomputer that was built to help be a resource for Japan's industries of applying simulation and science to important problems. In fact, Fugaku itself, Japan has always led from the Earth simulator to Fugaku, solving really important problems for a nation. And during COVID, had one of the seminal simulations of understanding how COVID spread just in human interaction, being able to simulate it. So I think, Wahib, if you could elaborate a little bit more, what are the key lessons from how Fugaku has been applied and what you're looking forward to in Fugaku Next, which of course is on its way.
Yeah, good question. So in fact, the joint thread connecting all of these systems back to Earth Simulator and K and Fugaku and ABCI and looking forward has always been the very pragmatic position of what matters at the end of the day is real performance, the actual performance you get on real world problems, right? Or to rephrase it, you want to extract the most science out of the system, basically, right? And towards that, the key points I've always focused on in developing these systems, obviously co-design of the hardware with the vendor that has to happen closely from the beginning, from the inception of the idea throughout the process, such that you're involved, or we are involved basically with the vendor deeply in all decisions. That's for the hardware, and that's a given. And the important part moving forward, I think, which kind of changes things a little bit, is also the software, right? Maturity and stability of software matters a lot. Those are large systems, and you deploy them, they run for years. And again, if you want to get the most out of them, software stability and maturity matters a lot, especially as we mentioned earlier, as AI becomes more coupled with the hardware. AI gets more coupled with HPC. The software stack will get just higher, basically, not just wider, right? So when we say software stack, it's not anymore just the stack of the compilers and the libraries and the debuggers and profilers. We're speaking about the layer on top of that, which expects scientists would want to use to lower the entry bar for all scientists. And that's for a good example here is basically actually NVIDIA's effort for open libraries like BioNeMo, PhysicsNeMo, and so on. This is the kind of level of software that we think will help a lot, sit on top of the other stack. And actually it's much appreciated by us, and we look forward even to contribute to that. And moving forward, again, I think that's one main pillar we need to push forward, which is advancing software stack more and more, pile higher levels so we lower the barrier of entry, plus, of course, hardware co-design.
And having it all scale. I mean, trying to make a computer of 100,000 to 1 million GPUs work reliably.
That's true.
This isn't a Hero 1 environment. These are working, living scientific instruments that are working on incredibly important problems. And it's, the number one bug in a supercomputer is not the hardware, it's the bazillion software bugs that have been typed a long time ago, and we got to go find and explore. And actually, AI can help here. Thank God AI is at least a statistical problem. So as long as we build and design in resiliency into those frameworks you mentioned and others, there's hope that we can actually continue to use them and be resilient at having at a scale where things are just going to happen by the law of averages. The other aspect is it has to happen openly. Every one of these computers and this entire space is being invented in real time. So I'm excited that these frameworks are open. The other frameworks that NVIDIA is also contributing to, we have teams that directly work with, we treat them as our own. we treat PyTorch as Meta's, but we have our own team working on it, or JAX, or other foundational libraries across the board. Our focus is to make sure that the platform is productive across the ecosystem. And of course, Dan, NSF is now building a really amazing and exciting supercomputer, a long time coming. I'm super excited to see NSF investing along with DOE and, of course, now Nation. So perhaps you can provide, and NSF has a slightly different charter than DOE. I've always enjoyed the diversity of workloads that come across in NSF. So can you elaborate a little bit more on what you're looking forward to Horizon and some of the flagship projects that you're hoping to see come to life?
Yeah, so yeah, we're getting really close to Horizon, and I think the first time, like you and I talked about it, it's been almost 5 years since that first conversation. So
it took a while.
It's nice to see that point where we're actually starting to put racks on the floor
Exactly.
after all these years and getting close. And you actually showed the video about the characteristic science applications, right? Which are really the program we put together to make this sort of a forward-looking design, right? When we did our last really big machine, which is, we put up 6 years ago, but that means we set the specs and sort of locked it in 8 years ago in 2017, and the competition for it was based on benchmarks from 2006.
Right.
And when we actually started taking those benchmarks apart, we realized no one had touched the code in 10 years on at least one of them. And we used less than 1 rack of the system to run half the problems because they just didn't scale anymore. And to that notion of real-world problems that Wahib was mentioning, so we wanted to do is rather than sort of focus backwards looking on a benchmark, we wanted to focus on what our users wanted to do, and we really wanted to look at the whole problem for a number of reasons. One is it allows for innovation, right? It's not run this same stream of code from 20 years ago.
Right.
It's run the same problem, or at least a problem that you can compare to, right? But allow some flexibility in how you implement it to, there was no opportunity to incorporate AI with backward-looking benchmarks from when we started designing this machine in 2020. And obviously that's turned out to be really important in the way people want to use it. And if we have a machine that's, where again, we focused on one little part of the problem, maybe it takes an hour to run, but a month to bring the data in and a month to bring the data out, then no one really cares if it runs in an hour or 8 hours, right? If it's still 2 months to turn things around. So we wanted to look end-to-end across the workflow, and we wanted to allow some creativity and put all of our effort rather into tuning for an old benchmark to tuning for the problems that people wanted to run. And that led to that characteristic science applications program that you talked about. And we have started with about 150 problems that people proposed that they wanted to do on the machine. We've narrowed it down at this point to 11 that we're really focused on. That'll be the first set of problems to run in the spring on Horizon. So you mentioned 3 of them in the video, which I hadn't seen before, so that was exciting.
You look good,
but,
it was it was a nice walk down the aisle.
Yeah. So, but news to me too. So, things work as seismic earthquakes, multi-rupture earthquakes, right? Doing forecasts of, we have a fair amount of astrophysics. We have a fair amount of, molecular dynamics, like the work Ahmad does with NAMD, but it's NAMD plus the deep drive pipeline for drug discovery plus, so there's an AI component and a simulation component in some of those. We tried to get a sort of broad spread of science. But we've been able to, starting with the old system, with Vista, our Grace Hopper system in the middle, all the tuning has been focused on what can we do with these problems, even if we're changing the code. Some have moved from CPU to GPU in the time frame that we talked about, right? So it's not to run the same set of codes and then hope that that translates to the machine we build. It's to work on the problems we want to solve and build the machine to do that. Yeah. So we're really excited about that first set of problems. We'll probably bring back, the second wave of users will be, some of those Gordon Bell problems you mentioned, but, some of the earlier candidates that didn't make it into the final round, but who we worked with for a few years to get ready. And, not only does it give us a great set of benchmarks, it's given us the jump on getting the users to buy in on getting ready to use these machines for the problems they have instead of sort of, oh, here's the new machine, what do I do now, right? We started, in fact, with the 11 teams, we've now been working with them for 4 years. In about 3 months, it'll be 4 years since we started on those projects. So, and they're all ready, and that's really exciting. And we think we'll see, 15 to 20x the science throughput, right out of the gate in terms of the number of problems their labs are turning around versus where they were on the old machine.
It's all happening so much faster. And
Yeah.
as was mentioned, it's not just about the compute, just about the flops. I mean, it's nice. I feel like we're closing out the era of exascale with a bang with Jupyter, and it was. I'm thrilled that we got to there on the list. But like you said, the procurements, the new systems are moving from just having, here's a new system with this much compute, have at it, to actually thinking about workloads. And the workloads, which of course need the compute, but as you said, also will generate a lot of data. So what is the data strategy? They're generating the data? Can they consume the data? Do we have the data to operate? And then finally, AI is an algorithm, like being more flexible about how to solve the problem rather than being prescriptive of the amount of flops to run a problem. And as you can see, that's the same is true in AI. You can put a chip with a lot of flops, but you have to be able to have them all communicate. You have to want to apply the latest algorithms. That will get you the best possible system for the science. You can, we can't predict where it's going to be in 1, 3, 4 years' time, but at least you're setting down a path where the algorithm, you're giving a full canvas of the algorithms to deploy, which I really appreciate. But of course, there's not just about AI and simulation, it's also quantum. When I was in Germany, got to see the 2D wave, the systems that you have, as well as some of the other quantums, and Jülich is probably pioneering how HPC and quantum computing is going to come together in the early days. So I think, can you, given not just the simulation work, but also getting to experience and touch some of these systems, can you give the audience a little bit of perspective? How do you see this playing out? A quantum HPC combined world. What is Thomas's perspective?
Yeah. I believe that and I believed it very early, about 10 years ago when we started all of this, that quantum computers can only be fruitful finally if they are an integral part of an HPC system. Anyway, they need front-end systems to be operated, so they need digital components. But the real question is how a user can just write a program where, when it is necessary, a quantum device acts, or many quantum devices act, or even quantum devices act coherently, hopefully in the future. So that's what we believe, and we have several examples so far where we see huge progress. I should distinguish between the different categories. There are these quantum simulators or quantum, let's say, emulators, like we had just made some huge progress here, touching 50 qubits on a digital machine. This is for validation and for constructing new algorithms. There are also different varieties of quantum computers, like annealers, like they also call it quantum simulators, like the Pascal machine from France. Here I see huge progress on a short term. We will probably see lots of real problems being solved with annealers very soon. But of course we have more trust that all of this will converge, also the annealing technology, into more gate-based machines, not just those that we have today, which are these noisy type of machines, but those that have logical qubits. Right. And here we believe in progress on a scale of 4, 5, 6 years, that with a few logical qubits, more than 50 logical qubits, there you must finally see, if they are good enough, you must finally see the solution of problems that classical computers cannot do, but that are part of the work that we need to be done when we do something on classical computers. And here we see the convergence, when we can talk about the convergence of both technologies, that they come together and will be used in a coherent manner on classical quantum type of applications.
Well, we're at 1 logical qubit today, from what I can tell. So I think getting quickly to multiple logical qubits will, like you said, very quickly demonstrate a real working combined hybrid supercomputer. To close out, I wanted to give each member of the panel an opportunity to address what are the critical needs right now in AI and HPC. You have an audience here of people that are leaders in supercomputing, and I'm sure no shortage of grad students and PhDs to be written. Where do you think the community should focus right now? And what are some of the, whether it be libraries, algorithms, supercomputers, or more broadly to the agencies that are helping fund and having the courage to build them? What are the critical needs right now in HPC, AI, and quantum? And Thomas, if you could go first and go down the line.
So maybe you would call me conservative, but I believe our biggest problem will be in the future that we maintain, that we curate, and that we go forward with the numerical libraries, with BLAS, etc. So we need some huge community effort that these things don't become old and that they can be adapted to the new technologies to come. And here I believe is much to do because these underlie any type of activities that we do in supercomputers.
Very good. Jini?
So I'm going to build on what Thomas is saying a little bit, but a couple of things come to mind. One is curation and maintenance of the data deluge that we're going to see from our various different scientific applications, whether there are experimental facilities at DOE or otherwise, whether simulation-based or whatever it is. For any AI systems to be able to use it, the usable data compared to the data that we have on the floor, that percentage is just so minuscule and tiny, it's going to be a big challenge for us to make those actually usable for these systems. And then, of course, like the scientific applications historically have been focused so much on HPC-type systems. How you bring those scientific applications along in a changing systems world is going to be one of the biggest challenges that we're going to have to deal with.
Absolutely.
Yeah, I think both great answers, but I would say, right now we're seeing this sort of unprecedented scale investment in AI where all of the hardware you're building for us, right, is really focused on sort of the commercial AI applications and optimized around what their needs are. And in their current stage, they're in an environment where they're willing to spend a great deal of money to get the best performance out of that. In the scientific computing world, even though we've built giant systems, they were never actually big enough for the problems we wanted to solve. So we've always sort of lived in this resource-constrained world. And we need to sort of take that notion of resource-constrained and apply it to mixed precision algorithms, to emulation, and to all the things that it's going to take to exploit this fantastic hardware you're building to get performance from it in the most efficient way possible. And it's not only going to be critical for AI, it's going to be how we keep pushing scientific computing forward as the hardware continues to evolve. So that's, if I get one thing, I'm going to take that one.
Thank you, Dan. Mohamed?
Yeah, so I guess there are many challenges and they were covered, but I guess one point to add is while there's a lot of alignment in the HPC community and we can be pragmatic and building on what we see in the AI commercial space with respect to the tooling, the algorithms, the models, one also has to acknowledge that it's a little different in many cases in science. You need to extend the capability of AI beyond what you have in commercial space. It goes back to the nature of the data itself, is how you collect it, the measurement noise, high dimensionality, non-structured, skewed, non-IID, et cetera, et cetera. So at the end of the day, the data is representing some laws of physics, and laws of physics do not care what the model wants. You're not just collecting data from the internet. So that means a lot of effort has to be there. Similarly speaking, some stuff you study is just basically very long, cosmological or material decay and so on. And then nature doesn't care about the context of your model, the context length and stuff like that. So there's a lot of similarities, but also a lot of divergence. I think in that regard, it will take a lot of effort, community effort, as Thomas said, to try to take AI into the space of science, work on build what exists, use it, that's good, be pragmatic. What doesn't, you have to build that, and I think there will be a lot of mountains to climb there.
Well, all great answers. And as someone who gets to enjoy and learn and both the pile of technology that NVIDIA seems to be building or inventing, the libraries and what the ecosystem creates, and also the problems are never fully solved. There's always, the supercomputing, if there's one thing they're good at, is it's never a fully solved problem. We're always pushing toward the next step and next step and next step. My only ask is that you guys keep challenging, keep celebrating. Our company and everyone here is excited to work in this area now. And the more we can identify those opportunities, the more we can pull those. Supercomputing can be that continue to be that conference where it creates those challenges that pulls the whole industry forward. You have, I think, should fully respect how much this community has made possible the AI revolution today, the accelerated computing revolution, and all of the innovations, and it's not going to stop. So keep challenging, keep pushing. It's always inspiring, and I look forward to continue working in this space for as long as I can professionally do so. So thank you guys, and thank you everyone for coming to this keynote panel today. It's been really fun.